Honored to be here. Shaoshan Liu from Perceptin. In the past 4 or 5 years, I've been working on autonomous driving and robotic technologies. And then in the past 2 years, we've seen tremendous progress in this field, in this sector. We've seen big firms say Waymo, Google, Baidu, for example, Uber, doing their own autonomous vehicles. But then when you talk to engineers about building autonomous vehicles, they get scared away because it's so complicated and they don't think they can build their own autonomous vehicles. Hopefully with today's talk, I can convince you that you can easily build your own autonomous vehicle or autonomous robot with a modular approach using off-the-shelf components with a budget less than, say, $40,000 US. You can easily build your own autonomous vehicle. And by autonomous vehicles, I don't just mean the vehicle that runs on street, the commercial vehicle that runs on street. I mean all kinds of autonomous robots. It could be a pod that carrying 2 or 3 passengers within a campus environment. It could be an autonomous vending machine, or it could be an explorer tank that do rescue tasks in the forest and so on. So today's talk is going to be divided into 2 parts. In the first part, I'm going to fly through all the technologies involved in autonomous driving so that you know why it's so complicated to do it. And then in the second part, hopefully I can convince you that using a modular approach, you can easily build your autonomous vehicle. So first of all, autonomous driving, what are we talking about? Is it just one technology or what is it? Well, it's actually a very complex integration of many pieces of technologies. Let's just focus on the pink part here, which are the algorithm parts. There are 3 stages for the algorithms. First of all, how do you sense? How do you grab data from the environment? What kind of sensors do you use? GPS IMU, that's what you use to get the location of the vehicle. LiDAR, you can create a map with LiDAR, you can do a perception with LiDAR and so on. And then you have camera, of course. Camera, you can do a lot of perception tasks. Once you grab enough data from the environment, the next stage is perception. How do you understand the data that you just generated? For one thing, you need localization so that you know exactly where the car is at the point in time. Second of all, you need object recognition. How do you recognize all the objects that you encountered? And then object tracking. If you see an object in front of you, what is the next action the object going to take? You need to track it. And then once you understand your environment, you need to make decisions. First of all, path planning. How do you command your car to drive around the campus, for example? How do you predict the action of other objects in the environment, and so on? And then underlying that, you see a blue part, which is the system. To integrate so many pieces into a system, you need a very good operating system. Usually people use a ROS-based or modification of a ROS system to do autonomous driving. And then underlying it, you have the hardware platform. NVIDIA has the PX2, Intel is rolling out its own platform, and then there are a few startups in this space doing their own chips for autonomous driving. On the right side, you see the cloud platforms. Well, yes, there's a huge cloud supporting all these autonomous vehicles for it to work smoothly. For example, you need to generate the HD map, the high definition map. You need to model training, you need to do simulation to test your algorithms. And last but not least, you need a huge amount of data storage. Let's go over these components to see why is it so complicated. First of all, localization. How do you localize your vehicle in real time? If you just go out to, say, a street in San Francisco, how do you localize yourself? You use GPS. Same concept applies to an autonomous vehicle, but a different kind of GPS. It's called RTK, GNSS, such that it can get down to centimeter level accuracy. Usually the GPS in your phone can get you down to, say, 1 meter to 5 meter accuracy. But if you have open sky, you have a RTK GPS, you can actually get down to centimeter level. And that's what's required for autonomous driving. But that's not enough, right? Because sometimes there are buildings around you. Your GPS signal gets blocked. That's why you need LiDAR and HD map. So the concept behind LiDAR HD maps, you have this very expensive sensor called LiDAR, about $80,000 piece, that you can generate depth information from the environment. And then you stitch up this information to build a map that's highly accurate. You can get down to 5 centimeter accuracy with a high-end LiDAR. But then it's very expensive to get the equipment and to build the map itself, as we will explain later. So for the map, it's a layer map. Today, when you see a Google map, you have a ground layer that's from satellite data, and then you build on top of it using some semantic information. But then HD map, the ground layer is different. It's generated by LiDAR, such that you have a small grid of 5 centimeter by 5 centimeter. And then on top of that, you can add more reference line information, your name information, and then semantic information, and so on. There's a different way to do localization, much cheaper way. It's use your camera. Technology is called visual odometry. You use 2 cameras, for example, to generate the depth information. And then as you go from frame 1 to frame 2, you see how the points move in the frame. Then you can infer your location using this technology. And then sometimes people add IMU units, inertial unit to it, such that you can fuse the vision unit and the inertial unit to generate a highly accurate location in real time. So that's localization. Second part is perception. Pretty much when we talk about perception today, it's mostly deep learning based. And that's why NVIDIA chips works very well, because the GPUs are very good for training and inferences. For example, if you want to grab objects out of the frame, you can use fast RCNN or SSD kind of network to do inference. It's fast, it's accurate, but it does require a certain amount of computing power. Another thing you also need is semantic segmentation. Besides recognizing people and vehicles from the scene, you want to know, oh, this is the open space I can travel on, that's the pavement. You cannot drive a car onto the pavement, so there are different kinds of networks for semantic segmentation, such as PSPNet, which is a very good network for segmentation. Again, it puts tremendous pressure on the computing device. Stereo matching, you want to get the depth of an object. Say you detect person in front of you, you want to know how far the person is away from you. There's a content CNN kind of network that you can apply for these kind of tasks. And then also you want to track the movement of objects. Then in conventional computer vision, we use optical flow. Then there's a flow net for optical flow. So pretty much for perception, everything can be done using deep learning technologies. So now you know where your car is. Now you understand your environment. Next thing is planning control. How do you plan your route? Say if I want to go from point A to point B, how to find the optimal route to go from point A to point B. It's a very complicated architecture. This is the brain of the autonomous vehicle or robot. There are 7 layers. First, there's an interface with perception, so that you know what's around you. And then you have a prediction module that takes perception result as an input and predict the action of other objects, so that you can plan accordingly. And then for map and localization, that's the position data gets into the routing module. The routing module will generate a route. Then afterwards, all these data go into the red box you see here. It's divided into 3 layers, behavior decision. So do you want to follow the car? Do you want to stop? Do you want to yield? That's the behavior decision. Then it goes into motion planning. Then it goes down to feedback and control. And that's the advantage of all the car manufacturers, say GM, Ford. They're very good at feedback and control. But if you talk about behavior decision, say Google, Waymo, Uber, they're very good at behavior decisions. That's the interface between traditional car manufacturers and internet companies. Lane routing. When we do routing on Google Map, it's easy. You go from Avenue A to, say, 2nd Street and so on. It's a street level routing. But then for a car to navigate around the environment, you need lane level. You need lane information such that the car knows exactly which lane it's traveling on. So it's different kind of routing, but it's a similar algorithm, Dijkstra's algorithm, A star algorithm, and so on for lane level routing. And then the whole pipeline goes downwards. You have different scenarios. Say there's a master vehicle scenario, we design how you will navigate around the environment. Then there's a scenario designed for the car in front on your left, and so on. There's a cross street. You have to go through all these rules before you can generate a very good path plan. So let's do a very short cost breakdown for a normal autonomous vehicle. Usually the demo cars we see today, either Uber's car, Waymo's car, cost anywhere between $400,000 to $500,000 to build. Why is it so expensive? Look at sensor. The sensor itself is more than $100,000 usually, especially for the LiDAR components, $80,000 a piece. That's why it's so expensive. The hardware cost, usually if you use NVIDIA PX2 series kind of chip, $20,000 US, $10,000 US. That's the basic cost. And then the map, HD map, it's extremely expensive to build and maintain a HD map for 2 reasons. First, you need a very expensive equipment to go out to the street to scan the map. And then you need a very good cloud infrastructure to stitch the map together to generate an accurate enough map. And there's actually a 3rd reason behind is that when you use a Google map, it gets updated maybe 6 months, every 6 months. But then for HD map, you need weekly update to get the updated information. And that's why it's so expensive to build and maintain a HD map. Well, now we have learned that it's very complicated task to build an autonomous vehicle, and it's very expensive. How about this? It's a Bugatti car built by Lego blocks. So what about we use a Lego approach to build an autonomous robot or autonomous vehicle, such that we divide the vehicle into different components, and then we stitch the components together to build a special vehicle for different situations. And then we can use off-the-shelf components. Let's see how we can do that. So that's a car we built, anywhere between $30,000 to $40,000 to build this car. And then we kind of divide it into different components. On top of it, we have what we call a dragonfly sensor. It's a vision sensor, use computer vision to grab data from the environment for two tasks, localization and perception. And then we have RTK GPS modules, such that you can get very accurate location data. And then down there, we have the sonar and radar. That's for passive perception, such that if your camera does not detect an object, and then the object gets close by, it will be caught by the radar and the sonar. And the radar is for mid-range detection. Sonar is for the last mile of defense. And then you have the chassis. What's missing here in the picture is inside the car. There's planning and control box. Remember, we just go over the planning and control algorithm. How does it generate a path from point A to point B? There's a control box inside the car. So that's the basic building blocks. Let's look at the basic building blocks from the other angle. So we have GNSS for localization. We have this RTK GNSS module. It feeds data into the computer vision module, which is the dragonfly sensor here. And the dragonfly sensor, on one hand, it takes the data from GNSS and fuses the data with computer vision and generate real-time location update. So that's localization. And then for active perception, using computer vision, we can generate object type, how far the object is away from the car, and so on. So that's active perception data. And then we feed all the data to the planning and control module. So it generates a plan and command to command the car to go around the environment. Down there, we have a CAN bus, which is a communication protocol to connect everything together. Then we have the chassis. That's the car itself. You can have different kind of chassis. For a vending machine, you have a vending machine chassis. For a pod, you have a pod chassis. For a tank, you have a tank. So this is the differentiation between different applications. You swap the chassis. Then for passive perception, we have sonar and we have radar. And then let's look at these parts one after another so that you can understand how they work together. First of all, it's the upper part, the perception and localization pipeline, which is the combination of these two modules. Well, the first module is easy. It's just you have two receivers, mushroom receivers. That's what we call it. It's basically two antennas to receive GPS signals. Because you have two receivers, you can kind of tell the orientation of the car, because by looking at the angle difference of these two receivers, you can tell the orientation of the car. And then one receiver will receive the normal GPS signal, and then second receiver will receive what we call the correction signal from RTK GPS. And then you put this onto the car, then you have a basic localization capability. It generates two things. First thing is the real-time location of the car. The second thing is real-time orientation of the car, because the heading and orientation is very important when you do planning and control. But then, like I said before, if you are going under a building, the signals get bounced, such that you don't get very accurate localization results. That's why we use computer vision in this case. Here we have a full camera design, two looking in the front, two looking in the back, so that you get kind of 360 view of the environment. And then it generates two things. First thing is that using visual odometry, which we've just gone over, it generates the real-time localization data. And then you can fuse the data with GPS to give you very reliable localization. And then second thing is perception. Let's look at a very short demo. We have a few more demos, video demos, such that you can easily get the idea. So that's the full camera design for the Dragonfly module. Remember two functions, localization, perception. And then we have an interface to GNSS such that GPS gets consumed by this module. And computing is done inside the module itself. So this is a car that we deploy in an industrial park, kind of a controlled environment such that you don't get too much traffic. First experiment, let the car go around a big loop, probably 1 kilometer to 2 kilometers long, and we try to see how good the VIO is, how good the localization result is, using only computer vision. On the left side, you see the real-time road condition generated from the camera. On the right side, you see the trajectory. So as it goes around this big loop, its IMU unit or inertial unit is giving you an initial update, and the division is going to do the correction based on the feature it sees. By combining these two sensors together, we get a very good VIO trajectory. So that helps a lot, because when you have a vehicle autonomously drive itself in the environment, location is very important. The second part is perception. So on upper left, you see the real-time situation. Upper right, you see SSD-based detection, deep learning-based detection. Then on the lower left part, you see the depth information. At the end, you combine two information to extract target information distance, and then obstacle distance, and object type, and so on. For example, as people cross the street, you can detect there's a person in front of me, and then that person is, say, 8 meters away from me. And this is all done within the unit, so you don't need extra computing power to do it. So good, now we have one module that combines localization, we have one module and perception, active perception. So that's done. The second part we're going to look at, okay, now what if we need reliability, right? What if one module fails? Say if you fail to detect a person in front of you, what do? You have two more lines of defense, the sonar and the radar. And the sonar covers the mid-range. By mid-range in this speed scenario, say under 20 miles per hour kind of scenario, it's 15 meters. That's the mid-range. And the short range is 3 meters. When you detect something in the short range, you brake right away. So let's look at radar. How does it work? So you can install one radar in front of you. Basically covers a 10-meter range, 10 to 15 meters, depends on the kind of object you're detecting. And here there's a person crossing the street. You can do tracking. If you can see there's a small tail following the person, you can do object tracking using this technology. And now if there are two people crossing the street, you can track both people. And then for large object detection, such as a car, has a bigger range. So reliable in 15 to 20 meter range. So that's mid-range detection. You can use the mid-range for active perception or passive. For active, meaning that you can still have time to give command to let the planning control module to decide what to do next. For passive, it means it does not go through the planning control pipeline. You detect something, you stop. That's passive perception. So usually for passive detection with sonar, that's really the last line of defense. You detect something in front of you, you stop. So now we have a sonar pair. If we place it in front of the car, you can have a range like that, 3-meter range. If you detect something there, you stop. You shut down the car, you brake. See two targets over there because there are two sonars detecting things together. So we've been going through the computer vision part, the passive perception part. These are the eyes of the vehicle that can detect your environments. Let's go over the brain of this vehicle. The brain is the planning control module. Basically, it's an independent computer with algorithm built in, with well-defined interface. For example, if I can define a very good interface, that's localization, that's a timestamp of the object. You feed this data through the interface to the computing module, then it can make very smart decisions about where to go, what to do next, and so on. It's very interesting work. So it's very hard to show you a real demo because you will not know what's going on. So we did a simulator, but all the algorithms used in the simulator are actual algorithms. So we grab a map from my alma mater, UC Irvine. Say if you have the car deploying in UC Irvine and have it go around the campus, how would it behave and what kind of action can you do? So very first step, you can import data from Google Map or you can import data from OpenStreetMap and so on, different kind of maps. That's enough for us to do navigation. So there's no need to rebuild the HD map. So here you can select the starting point, you can start the destination and the stops in between and have the car just go over this route. There's several basic functions. The first one is called cruising, the cruise mode, such that you follow your lane and then you go from point A to point B. And that's the cruise mode. On the upper left, you see the real-time speed of the vehicle. Remember, all the algorithms used in this simulation is actual algorithms that we deploy in the car. The simulation is to just show you a demo of how the technology works. So in this kind of scenario, there's some basic function you need. First one is cruise, of course. You need to go from point A to point B. The second thing is what if you saw something in front of you? That's obstacle detection. So the perception pipeline feeds it the signal. Say, hey, there's someone in front of you crossing the street, then you stop. So that's dynamic object. How do you deal with dynamic objects? And then as it goes through the environment, it's a long demo, sorry, because we do it in a real-time speed, 9 kilometers per hour. Then you might go into a car merge scenario such that there's a car in front of you gets pulled in. Then we can do a second function, it's called car following. So if there's a car in front of you moving at similar speed, you can just follow that car. We have a demo of that pretty soon. So there's a car in front of you, and then you pretty much just follow the car. The way to do it is that we can detect the distance from the obstacle in front of you. You just kind of maintain the distance as long as both objects go through the same route. And if that stops, then it becomes a static object, such that you can go around it. That's the third function. If you detect a static object, you can safely go around the object to continue your path. So again, this is an actual map from UC Irvine campus. And then that's a static object detection. Say there's an object in front of you, then from the perception pipeline, we can tell whether that's a static object or it's a dynamic object. And this is in slow motion. If it's a static object, we can easily go around it. But if it's dynamic, in this kind of scenario, we can stop and wait for the object to go away. So that's very interesting because there are 3 types of objects that you can detect. One is the car in front of you, you can follow. That's a very smart decision to follow the car in front of you. And then if it's a dynamic object crossing the street, you can just wait for it to cross. And then if it's a static object, then you can go around it. It's all smart decision built into this planning and control module. Then once we reach our goals, reach the destination, the very last function that's required is the parking. It finds the nearest parking lot and it parks itself. So here, there's a charging station, if you can see over there. It goes over there and parks itself into the charging station. These are electric cars, so it needs to be charged. So that's actually how it would park itself. It gradually finds the free space and then pulls itself into the free space. Again, the algorithm used in this simulation is exactly the same as we use in the physical environment. So that's it. That's all you need to build an autonomous vehicle. You need a brain, the planning control. You can actually develop your own planning and control algorithm. And when we talk about planning and control, there are several things, right? You can follow the car, you can do cruise, you can do parking. And then you need good eyes for the car. So you need computer vision, you need GPS to do localization. And then for the vehicle to be reliable, you need another line of defense, such as sonar and radar. That's it. That's pretty much it. That's all you need to build your own autonomous vehicle. And then we have 4 cases, 4 solutions that we built internally so far. We have a pod that you just saw. We have an Explorer tank that we built last year. We are building a vending machine, very interesting user scenario. Say if we can have an autonomous vehicle that's vending, if there's a kid in front of you, wave at it, then it stops. You can buy a can of Coke, or you can buy anything you want from that autonomous vehicle. I think that's a very good application. At the end, we also built a drone, a large farming drone equipped with Dragonfly module, such that it can do localization, it can do perception. We hope that by providing this basic technology, we can enable people to build more robots, different kind of robots or autonomous vehicles. It would be very fun to using this Lego approach to build your own autonomous vehicle. Again, for more information, there's a website. All the parts and demos are up there if you're interested. And that's the end of my talk. I welcome any questions we can discuss. Sorry, can you come up here? I couldn't hear you. Yeah, maybe you need this microphone here.
So real time, there's inference happening and decision making about planning the module, right?
Yes.
You mentioned the Jetson, the NVIDIA Jetson is what you're using, which is more like an embedded.
That's a very interesting question. Actually, yes. Jetson is an embedded grade kind of module. So we did a lot of optimization on Jetson to make this work, to make localization work, to make perception work. Because if you look at the NVIDIA offering, there's a Jetson, and then there's PX. If you jump to the PX grade series of chips, that's like $20,000 US. I don't think that's a very good option for us. So next generation, we are actually moving all the algorithm into a FPGA. First thing, it's much cheaper. Second thing, it can deliver much higher performance. Third, power consumption is lower. So today we see nowhere in between. There's a Jetson here for embedded. There's PX there for fully autonomous, but it's extremely expensive. There's a whole gap here that no one fulfills. Go ahead.
Could you talk a little bit more about the FPGA move? Are you using like Xilinx FPGAs? Like, what's your implementation plan?
Well, we use the Xilinx Zinc series, so it's a $100 range FPGA. So for robotic, any kind of robotic workloads, we see there are only, or to us, there are three major functions, right? First of all, perception. How do you recognize things in your environment? So if we can put perception into hardware, that helps a lot, especially on the frame rate. So we can do, say, 30 frames per second. The second thing is localization. Using VIO, for example. We also want more than 10 frames per second performance to give you very accurate data. The third part, I'm not sure that requires FPGA, it's planning and control. CPU works very well with planning and control. So as a next step, we are putting perception and localization into FPGA, into the camera module itself.
Just as a follow-up, what kind of frame rates are you seeing with the FPGA? Is there a latency problem with like the size?
Much smaller for latency problems. With, say, Jetson, maybe there's it's more a frame rate problem instead of latency problem. Okay. We are seeing about, say, 3 to 5 frames per second perception on Jetson. But we are expecting, for high-speed scenario, of course, we are expecting 30 frames per second on FPGA, and that can be achieved. Oh, yes. I think the only open source software we use is OpenCV that provides basic function. And then for operating system, we built our own operating system. Because ROS to us is too heavy-weighted. There's a lot of overhead. Especially we're porting everything into Jetson. It's an embedded system, so we built our own operating system. Well, that's actually easy to us. For all the FPGA, there's a function called, not many people use it, but there's a function called partial reconfiguration. You can, in runtime, reconfigure a part of the chip within, say, 2 milliseconds of latency. So it's really easy to do an update using partial reconfiguration.
Oh, wow. Could you do that between planning and localization cycles if you need to?
I don't think you need to do that within a cycle. It's too dangerous. Yeah. Well, most of the open app you have today, say Google Map, OpenStreetMap, it's accurate in big cities such as New York, right, or San Francisco. But in rural areas, they may not have enough data. In that case, you might want to do your own scanning. But say if I scan the campus, for example, scan the campus of UC Irvine, it takes maybe half a day to do scanning ourselves. And then because when we scan, we use RTK GPS plus Dragonfly for localization. So when we scan, the data is very accurate. That's why we determined it may not be necessary for us to use HD map. And it's too expensive for us to use HD map. And then it's still an open question, who's going to pay for the HD map if we really deploy autonomous driving? All right, I think that's it. Thank you so much.